Hi, thanks for coming. Oh, okay, now thanks for coming in. Last day before the spring break. Yay. So we'll talk about the third way that stars can end, and that is black holes. So we had, so I've put all the slides before this on there as well, so I can rapidly skip all the way there. We've had neutron stars, really dense. Basically take a whole 747 and stick it in a grain of sand. It's something, one solar mass is the size of Louisville, or we take the electrons actually hold out. So we have something like two 747s in a Coke can. That is a white dwarf. So these are still, they're still physical things, and they're, but the pressure hasn't fully won over. But what happens now, of course, I have all these animations, so let's skip past all of them. So the last kind of sort of end of the star's life is that nothing can save you. There's basically either electrons are keep their elbows out enough to keep the crystalline, so you end up like being a white dwarf, which is essentially a giant diamond. Or you end up with something where the electrons get pushed into the nucleus, and so it's just made out of neutrons, so you get a whole ball of neutrons. And there could be that the pressure just is too much, and so you keep pushing until everything is down into a point. And that is what a black hole is. So if you have a large enough star, you end up with a black hole. And yeah, what's the evidence for this, right? So black holes are, I think, the most favorite topic of every class that I've talked to in my kids' elementary school and like middle school and what have you. They've seen this movie where there's planets around a black hole. Kip Thorne actually was one of the people that helped with the visualization, and so this is what a really massive black hole for the interstellar actually looks like. There's also a really bad movie called Event Horizon, and that's the term that I want to introduce you to now. So the actual black hole itself doesn't have any size. Basically, all the mass got squished into a point, because the gravity just keeps winning until it's a point, except there is sort of a point of no return. So there is a sphere in space that has a certain size, and that depends on the mass. So if I want to call that is the event horizon, or also known as the Schwarzschild, after the person who figured it out, the Schwarzschild radius. And so that radius is 2 times the gravitational constant, so it just depends on the mass divided by the speed of light twice. And so that ends up being about 3 times the mass of the black hole in solar masses. And then that's the size in kilometers. So we've been talking about things the size of our solar system, things the size of our planets. So if you have like a red dwarf, a red giant, it will blow up until it's the size of the inner solar system. A white dwarf is the size of our Earth. A neutron star is the size of basically the 265 ring. And now we have something that you take a single mass star and you compress it all the way down to a black hole. Its Schwarzschild radius, basically the point of no return, is only 3 kilometers, which is 2 miles. So the size of campus. We've now got, we've compressed it all the way to that, the mass sits on my fingertip, and then you would notice that you were in a black hole, or you wouldn't see this until you got to campus, basically. So if I go, a black hole, the solar mass has a Schwarzschild radius, and please bring out your voting cards, of the Louisville Beltway, the Earth, 3 kilometers, or infinitely small. So what is that Schwarzschild radius for a solar mass black hole? This is the equation to figure that out. Voting 1, voting 2, voting 3. Mostly see 3 kilometers, right? So this is now, yes, I do everything in kilometers, not just because I'm European, but also because science talks in kilometers and meters and the system international. So that makes makes finding a solar mass black hole, like stellar mass black holes, really, really difficult. Can you spot it on the screen? Because it's black, absorbs literally all the light, and it's 3 kilometers across. It's hard enough to spot something that's 3 kilometers across in our own solar system. Never mind many, many, many solar systems over. Right? So if I'm looking at something like this, you can only see it because the light is being bent around it, or if something collides with it and manages to break apart. Other than that, this is sort of the only evidence we could get if we were just looking at light. And remember, I don't know, 7 weeks ago we were talking about light. 6 weeks ago we were talking about light. So if we learn everything we can from just the light that we can observe, a black hole is the worst because it absorbs everything, doesn't emit anything, and the only thing that it does is bend a little bit of light around a 3-kilometer little thing. So unless you're really, really lucky, you never see evidence of stellar mass black holes. These were almost impossibly directly to prove, right? So how did we actually know about them? This is the part that I want to talk about that, right? If anything falls in, if it encounters something, it basically falls from an almost infinite height, so it gets a lot of energy before it hits the black hole, and it doesn't all hit at the same time. So for example, if a stellar mass black hole has a companion star, and a lot of stars tend to end up being in binaries, and so this one has turned into a black hole. This was a massive blue star. It blew up. It shrank all the way to a black hole, and then it starts essentially siphoning off the outer parts of the companion star, and they start falling into a disk. You get a jet. So that is very energetic. That emits X-rays. So these are called X-ray binaries. So that was the first kind of indirect evidence of seeing a stellar mass black hole. They make for excellent artist impressions because you basically describe it to somebody who can draw, and they come up with something like this, right? So there's a companion star, they're close together, you see the stuff sort of fall into it, and then the jet of X-rays coming out at either end. There is other direct evidence, fairly direct evidence for black holes, but this is the one in the center of our Milky Way. That's much larger than a stellar mass black hole. But if you can see where stars are, and see, look at this guy. It's orbiting something, and there's nothing there. There's no star there. That's an O star, by the way. Like, that's not a small thing that just whipped around on a dime. So we've been looking for the stars in the center of our Milky Way. This is a different set of pictures. Starting in 1995, every year, sort of take a picture of where all the stars are, try to get that as sharp as possible. And you can see that a lot of them are orbiting around absolutely nothing here, right? So there's a Keplerian orbit. It looks like, look, it's an ellipse. It's like all the planets and the asteroids here in the solar system. And they whip around like that. So something's here, something really heavy, and something that's much heavier than nothing, and that is a big star. So that implies a black hole, because really that's the only thing that would be heavy enough to have a star like that whip around like it's a planet in the solar system. But it is, not a misnomer, a supermassive black hole. Many times bigger than a stellar mass black hole. Stellar mass black hole were one of those things that we were pretty sure they existed because we see neutron stars, we see white dwarfs, but we hadn't actually seen them other than a few X-ray binaries. So we had no idea how common those were. We had no idea how many of them there were, and certainly the supermassive black hole is millions or billions of solar masses. So you've got, well, we think we've got something like 1 or 2 and a billion, and everything in between is missing. So intermediate was completely missing. So how do we get there? And this is the part where I go from, rank them in order of density. We've got a black hole, so from least dense to densest. Black hole, white dwarf, neutron star, white dwarf, black hole, white dwarf, neutron star, black hole, white dwarf, black hole, neutron star. Which one is, go from least dense to dense, right? 42. 43. Got majority C in the room. Let's see, white dwarf, yep, the electrons are still holding out. Neutron stars, only the neutrons are holding out, and only just. And when even they can't hold up the pressure, then you essentially end up with a black hole. When the mass density is infinite, right? This is the part where physics sort of throws up their hands and gives up. We've just stuck over a sun's worth of mass in a point smaller than the period at the end of the sentence. Huh? So, as you can imagine, the normal physics sort of break down. But we can now say like intermediate mass star, so something like our sun, maybe a little bigger, maybe a little smaller, but yellow, becomes a red giant with a planetary nebulae and something in the middle. That's that white dwarf. And then if I have a high mass star, it becomes this blue supergiant. It also blows up as it starts going, burning helium. But then it goes supernova, and you end up with a neutron star. Okay, that one I can see. Or a black hole if it's greater than 3.2 solar masses in the core. Right, so there's two limits. If it's smaller than 1.4 solar masses in the core, I end up with a white dwarf. If it's just between 1.4 and 3.2, I get a neutron star. Neutron stars are not that common, and then even bigger than that, we get black holes. So most stars end up as white dwarfs. We see those things everywhere. Some of the big ones end up as neutron stars, and then a very few really big ones end up as stellar mass black holes. So what's the correct way to see the evolution? Red giant, neutron star, white dwarf, nothing. Red giant, supernova, planetary nebula, neutron star. Red giant, planetary nebula, white dwarf. Red giant, planetary nebula, black hole. Which one is the correct order of physics? Voting in 1, voting in 2, 3, still got majority C, fantastic. Okay, so that's the evidence I have right up to a few years ago. This is also a fun one to just talk to all you, to just tell the story, because if you ever talk to your friends about like, what's the evidence for aliens? Oh, I think they've already discovered this. Astronomers are the worst people to tell a secret to. We are absolutely phenomenally bad at keeping a secret. So there was something up, like a week, and it's like, yeah, there's a press conference on Monday, and everybody was like, I know what it's about, right? And so this was this whole scuttlebutt going on social media and what have you. There was finally a first detection of gravitational waves. And so gravitational waves is no longer detecting the light directly, and so this is what a gravitational wave telescope looks like. This is a mile long, and there's another arm going the other way. And this L-shaped thing is measuring essentially constantly the distance between the endpoint here and this building and the endpoint there at that building. And if a gravitational wave comes through, it actually warps all of space a little bit so it gets longer and shorter. So what does that look like? Well, this is what's happening. As you can imagine, all good science happens with giant freaking lasers. And so we're now in the giant freaking laser part. You have a laser, you have a mirror that bounces and splits the light going straight, and then one turns off. It bounces off the mirror at the far end and comes back in, and does the same thing here. And if these two wavelengths actually match up, so that means that if the distances are equal, they actually interfere in a way that they strengthen each other, or they cancel each other out. So if the mirrors at the end move by just a little bit, I can see that as either I get the light going all the way through or not. So if I measure the distances just right, and I see these things change, because that's the real measure that I'm trying to do, then I know that the mirrors have moved ever so slightly. So you can imagine that this is so sensitive that basically if a squirrel tap dances on the top of this thing, it's already going like, no. Or there's a truck going by on a nearby. So there's a lot of noise. And just to give you an idea, what we're looking for is something like this. Two neutron stars. So both of the stars turn a neutron star, and they are coming closer and closer together. As you can see, the waves are coming off that, right? Those waves is the ones that we're looking for. And right at the end, that big explosion, that's where the biggest wave comes from. So what we were looking for was something that that wave would arrive first, and then the light from that explosion would be something to look for. And so this is what it looks like in the actual gravitational wave. You can hear it's mostly noise. This is squirrels and trucks and what have you, right? So it sounds like a white noise machine. Right here, these things are getting closer and closer together. And the frequencies, they're spinning up, right? They're going faster and faster. The frequencies on this axis. Did everybody catch the little? No, not everybody. Yeah, my ears. I'm right here, and I have to strain to hear it. I can do it again. It's mostly noise, right? This is 30 years of people just listening to this kind of stuff, and then suddenly seeing two things go closer and closer and closer and closer. There. That was the first one we found. And we can also do that with two black holes, right? So if you have two stellar mass black holes or two neutron stars and they start merging, a lot of interesting stuff happens. They start warping the space around them. What you see actually gets warped. We don't actually know what's happening here. That was just too hard. It's not like there's a third black hole. It's literally like left out of the simulation as being too hard. So, okay. So a lot of interesting stuff is happening around it, but what's also happening is that you get these waves, that there's gravitational waves coming off of them, right? So after the first one was found, this is very typical in astronomy, as soon as we know the trick, we find them all the time. So as soon as the LIGO, this is what they're called, the Laser Interferometer Gravitational Waves Observatory, there's one in Louisiana and one of them in Washington State. And so for 30 years, they kept improving their instruments. This is, I don't know, that's a serious grind, right? You just go like, all right, now we need to get the noise out of this. Now we got to chase the squirrels off the roof. And now we're going to go make it polish the mirror to the point that it actually works down to what we need to do. And then once it's switched on, it started picking up these mergers all left, right, and center. So neutron stars merging together, and then also black holes merging together. And so as these things get closer and closer, they spin around faster and faster, their frequency goes up, so their wavelength, they start slow, and then it spins up quickly. So you look for those chirps, and that's what the merger looks like. It's called the chirp, because, because that might last a little while. As you can imagine, so you've had this probably happen to you. If you need to know and have your phone know where you are, it needs to be able to ping how many cell towers in order to figure out where you are. 3. You need 3 spots to figure out where you are. If it's just 2, you could be here, but you could be on a line between the 2 towers. And you've had that where it just, suddenly tells your friend is nearby, but it means all of Jefferson County all of a sudden, because basically one of the cell phone towers dropped. So have you had that? Find my friend kind of deal? Okay, so you need 3 to pinpoint your position, but we only had 2 telescopes to find them, right? So if we want to see where on the sky this is, you essentially get a line going like, well, it's somewhere along here. That's way too big to quickly search with a telescope, right? So what we really wanted to do is have a 3rd gravitational wave, so LIGO, and so Virgo is a European one, so then you have your 3rd tower, then you have your 3rd reference point, so you can actually figure out where on the sky this thing is. So it went from like, I don't know, somewhere in the south to here. And here is still a pretty big area, but it sort of looks like this. So this is the LIGO Virgo, one of those where they saw one of these mergers happening, and it's like, yeah, it's in here somewhere. And this is the part where this was not a completely open secret, because literally every telescope on Earth is open source. So it will tell you at any given time where Hubble is looking, where James Webb is looking, what have you. And all of them screeched to a halt at the same time and sort of started swung over to this galaxy. So it's like, yeah, it's not subtle. I think something's up. And so what we found was this little dot here in that, and so this is before, so we have before and after. We found the actual light coming off the merger of two neutron stars. And so every telescope, like notice that they all have these acronyms, Vista, VLT, what have you, Hubble, everyone switched over and looked at this galaxy. And so the Hubble Space Telescope, yeah, here we go. So if you look at a sphere, we looked with a high energy telescope that sort of got us like, it's in here somewhere. Integral looked at it, it's like, okay, it's in here somewhere. We have the Virgo thing is also in here. There it is. So here's the LIGO. It's in here somewhere. So you start narrowing it down. First with telescopes that are good for wide area views. It's like, all right, Virgo plus LIGO, it's in here. These are all the galaxies that are in there. All right, everybody check them out. And so that's what we've been doing. And that was the one that had an extra little light dot show up. And so one of the things that happened was that, where is it? Okay, so this gives you an idea of which telescope looked at it. I'll give you a hint, it's all of them. So this is how you know that astronomers will not, if we find a signal, if we find a radio signal of aliens or whatnot, everything will come to a screeching halt. Everybody will suddenly have their noses pointed in one direction because that's basically what happened. And so we're like, yeah, there's a press conference on Monday and we all don't know what this is about, except that we all swung our telescopes at exactly the same point, right? So to give you an idea, there's 5 in space, that's basically all of them. Here in South Africa, the ones, everything in Europe, basically, this is Canary Islands, everything in Australia, everybody swung their telescopes around, hoping to catch that little kilonova, that blip over here, and basically everybody caught it as well. And so the funny thing is, we had a Hubble picture before and after. And Hubble doesn't tend to look like this is the light curve, so we actually followed that up and saw that it actually dimmed over time. So it's days since the LIGO Virgo trigger, and we can immediately start looking, and yes, there was a dot there. So Hubble actually found it as well. This is the Hubble picture, and you can see the light fading over time. It's in 2017 that we found the first one. We also had a pre-picture of that. And how did we end up with like a random Hubble picture? And that was because a few months before, the Hubble snapped a picture of a part of a just random sort of like a filler program. So we had a pre and post image of the event, and that means we got just stupidly lucky because Hubble doesn't look at just everything. And so we had a pre-picture as well. So I want to overemphasize here that also in science, especially something like astronomy, sheer dumb luck plays a huge role, right? We would have not been able to pick that out as easily if we didn't have a pre-picture with Hubble as well. And so just to give you an idea, I think this is a full third of all astronomers on Earth were on the paper that found the light curve, found the follow-up. Science is a team sport. Yes, this got a Nobel Prize, but not all these people got a Nobel Prize. It went to Kip Thorne and Rainier Geis and Barry Barish. And Kip Thorne is the person behind LIGO. He's the person who kept pushing the National Science Foundation to go like, look, this is a multi-decade plan. We are going to improve our gravitational wave detector over time. I have a plan. This is how we get better. This is what we learn each step. This is 30 years of not finding squat. And then after 30 years, getting your instrument just right to then start finding these things. So yeah, that's worth a Nobel Prize, except that it's not just Kip Thorne building this thing, right? It is a full, it's a long shot that paid off, but it is in reality for the whole LIGO team. We actually distributed the prize money between the whole LIGO team. I have an issue with the Nobel Prize because it's limited to 3 people, and you can't give it to a team. You go like, but science is a team sport. A team of people will find the next big thing. A team of people has been working on this. This was a team of people that knew how to make vacuum tubes. A bunch of people who knew how to make really good mirrors. A whole bunch of experts in lasers. A whole bunch of people who, I don't know, knew how to make instruments really, really well. And so, yes, led by physicists, but with a whole team of people who knew how to make things. So we talked about it before that we find all our information from light. This is still mostly true, except since 2017 we now can add gravitational waves. These are literally ripples in space-time. So if you see like eventually you all grow a little taller and then a little shorter, for example, because the space is basically stretched out and compressed again. And so when massive things come closer together, they throw out really big ripples. And LIGO's been observing black holes and neutron stars melting together, right? So this is the kind of melts that they saw. They saw neutron. So these are sort of 20 under a few tens of solar masses black holes, and they merge into bigger and bigger black holes. And so the neat thing is that we can say, oh, this is how you get intermediate 100 solar mass black holes, 200 solar mass black holes. You merge smaller stellar black holes together, and then they grow even further. So this is the stuff that I wanted to show you for, that's our direct evidence for black holes. The neat thing is that if two stellar mass black holes like that merge, they throw out as much energy as worth about a solar mass. So there's a lot of energy that goes into that gravitational wave. That ripple is pretty big, and that's why you can pick it up in a completely different galaxy. The race is now on to see them further away, what we can use them for. But the first thing we learned was that, yes, stellar mass black holes exist. A lot of them are there. This is direct evidence, not indirect, as in like, well, there's something dark here and something's orbiting it, or something's falling in there. And so because it is the class before spring break, I figured we could do a group work, and then we have a show about black holes for the planetarium. Yes? All right. So stars end up one of 3 ways. You either end up a white dwarf, which is basically a smoldering corpse. You end up a neutron star, which is strange. It's one giant atom, but it is useful because it's a nice lighthouse of a lighthouse of a radio beacon, or it's a black hole, which everything sort of ends there. But some of the most exotic things in the universe are made in the death of stars. So if you're an extreme physicist, basically you want to see what happens if matter gets compressed incredibly, or you have really massive magnetic fields, or you spin something the size of the sun, a couple of 100 times a second, then you're interested in these things, right? This is sort of max science or max physics. This is definitely no longer the kind of stuff that we use for in our kitchen for physics. I think I can do it on that side. So we go back to Schwarzschild radius, I'm pretty sure. So I taught this class for the first time in 2017, so there was very much a like, well, so stuff is about to happen on Monday, and I think I have to revise the entire thing starting that week. So this was some of the stuff that came out. And so this is this is what I like about astronomy. Once in a while you have to go like, well, back up. I said we learn everything from light. By the way, this is an absolutely terrible movie. So if you have a terrible movie night with your friends, highly recommend Event Horizon. It is trash. It's just terrible writing. So if you like terrible sci-fi, it's just very clunky. It's just like, oh no, we're falling into the black hole. That's the entire plot. So they can be fun, right? This is why I'm like, yeah, there's like Interstellar is this heavy, humanity kind of thing, and this is like, yeah, oh no, we're falling into the black hole. That's it. So, yeah, that works. I think we're the one with the, I think there's two, but this might be the one with the threatening robot. I can't remember anymore. Okay. How was it? Yeah, I thought so too. There's two reasons I enjoy science fiction books. They're either really good and make you think about, the relation with technology and people, and it's just, good science fiction is back today. And then you've got really terrible where they didn't bother to really write anything, and so this is just a pitch. It's terrible. It's great. There's a dimension of infinite terror. Come on. I mean, I'm sorry. Oh. Sucked into sci-fi. How we doing? So it's 2.95 times mass. Not just you, make sure that you're working with your groups. So M and J's tend to be aged. Okay, so this is 2 times 9, 5 times anything, the mass expressed in solar masses, right? So the first question is 10, and you say 10 solar masses, so it's 10 divided solar mass divided by solar mass. So 10 here, so it's 2.95 times 10 in 4 masses. So the first one is 2.95 times 10, so it's 29 kilometers, so it's 10 miles. And then if you take 8 up here, so it's 2.95 times 10 to the 8 kilometers, which is 300 billion kilometers, which sounds like a lot. So that's the, if you express the mass in solar masses, it's like this basically is no ratio. Yeah. So this is, yeah, I always express the mass in solar masses, because if I do this in kilograms, it just gets twisted away. So solar mass is a useful unit. So it's the unit. At that black hole, that 300 million solar mass black hole, could you make that out of a massive star? The biggest stars we've seen are 150 solar masses. So even if the whole thing had collapsed into a black hole, we would get 150 solar mass black hole. So millions of solar mass black hole. How do you get here? It's more than 2 kilometers, right? You have to throw half a galaxy in there. So this is one of the I wanted to take you all to like, okay, you understand how black holes as stellar mass happen because of big stars exploding. But we don't know how you make something that's millions or billions of solar masses. How do you make something that big? Did you keep throwing stuff in, or did it all collapse in one go? So this is actually one of the new mysteries that we're doing. So I wanted to take you all to like, okay, here is a question that we actually don't know the answer to. I hated the science classes that were like, okay, here it is, and everybody figured it out in the 19th century. I'm like, okay, is there anything new? And it's like, here's like, this is what we're working on right now, to try to figure out how you make a million solar mass, 300 million solar mass, a billion solar mass black hole. How do you get there? So I figured that would be fun, more fun. All right. Time to switch everything off. Is everybody done-ish? Any other questions? Does this make sense? So if I give you a mass in solar masses, so I say like 10 in solar masses, like then you put 10 solar masses, the solar masses go out, that's the unit, so it's just times 10. If I say 10 to the 8 solar masses, is this number times 10 to the 8 in kilometers. 10 to the 8 kilometers is the size of our solar system, right? You're still talking about something that is pretty small on cosmic scales. So even if you have a really massive thing, it's still very hard to see it directly. What we have, and we'll get to that when I talk about supermassive black holes. And now we're going to do the planetarium, so I'm going to switch everything off and turn it over to Drew. And I think, who narrates this again? It's got that.
Oh, they'll recognize